Okay. All right. So here's, again, basically, so we got the real, the polar, and the complex exponential form. All right. We said we've got a problem in general with angles, right? If we're in the first quadrant or the fourth quadrant, everything's good. It's real part over imaginary part, or sorry, imaginary part of a real part to take the arctan. Now, the thing to remember too is B and A can be positive and negative, right? So if I told you I had 3 minus J4 is equal to Z, and I said, give me the angle of Z, how would you do that? Arctan of what? -4/3. The important thing is, the negatives go into that, right? So when you're looking at this, it may not be obvious, right? B or A can be negative. They could both be negative, right? And that's the problem with arctan. It's only defined over in these two quadrants. So what if I gave you -3 minus J4? Well, then it would be -4 over -3, right? What quadrant is that in? The third quadrant, right? And so in this case, what do I do? Well, I can add or subtract 180 from that. All right. So I can add 180 or subtract 180. Both of them are going to give you a correct answer. They may not give you the answer that the MATLAB system is looking for, but usually I tell you in the MATLAB system when I'm looking for answers, usually I tell you to give me the angle between plus 180 and minus 180. All right. You will need to pay attention to what that gives you. All right. So if I did it this way, what angle would I get? I don't know what arctan of 4/3 is. All right. Let's say it's somewhere around about 50 or 60 degrees, something like that. So if I did that, the angle that I would get would be what? I don't know. Let's say it was 60 degrees. It's probably close to that. So that would give me, if it was 60 degrees, it would give me 240, right? Right. Let's say it's approximately that. If that's true, and I put that in the MATLAB system, at least for the last homework, it wouldn't have taken that. It would have told you were wrong, even though you're right. Right. In those prompts at the bottom, it's telling you basically what, remember there's infinitely many angles that you could actually put in there, right? If I told you 240, that's the same as one angle. It could be 240 plus 360, right? It could be 240 plus 720, right? All of those are valid numbers. So I need to narrow it down to one particular choice. So instead of saying 240, I could also say that I could give you the equivalent negative angle. What would be the equivalent negative angle for 240 degrees? Well, -120. Yeah, right. I think that would be right. Negative, yeah, -120. Yeah, that would be correct. Okay. And you should be able to figure out how to make those manipulations. Okay. All right. So there's a good summary here at the beginning for all this stuff. Okay. Um, there's all this in terms of the angles and which MATLAB functions are useful to you. All right, as well as for the conjugate stuff, and then basically how to use the complex exponential in MATLAB. Okay. And then for addition and subtraction and multiplication division. Okay. All right. So with that, I want to kind of pick up on where I ended last time. So I talked about this idea of what we call Euler's identity, which is basically the way that I can take um, a complex number and I can relate it to the complex exponential. Okay, so what we said last week, we said if I have, so in general, a complex number is R, I guess the way I'm writing this is Z. I said Z is equal to the magnitude of Z cosine of the angle plus J magnitude sine of the angle. That's one way to write this. Using this thing called Euler's identity, I can basically rewrite this thing as Z e to the J theta like that. All right. Now that turns out to be really useful, like I said, in a lot of contexts. It's not immediately obvious. You can prove it. I'm not going to waste time on the proof of it. You can look it up in the book if you really want to know it. But I can use this in a lot of different ways to represent sine waves. All right. And that's where really it becomes useful to me, is in using this to represent sine waves. So last time we basically said, all right, well, if I plugged a negative angle into here, I get what I have here, which is to say, what did I do here? When I put a negative angle into this statement on the left, what happened over here? Right? What's cosine of negative theta? Cosine of theta. And when I took sine of negative theta, the negative sign spit out. Okay. So let's say I tried to add together e to the j theta plus e to the negative j theta. Right? If I add those two things together, well, what do? I add basically those two statements together. So if I add these together, so I added this statement to this statement, what would happen to the sine terms? They'd disappear and I would get 2 cosine theta. All right. Similarly, if I said e to the j theta minus e to the minus j theta, what would I get if I did that? The cosines would go away, and I would get 2j sine theta like that. So usually what I do is I say, well, I can also divide that by j, and I would get that. All right. So we basically derived those two relationships, right? The one that I end up with is, and that I usually deal with, is this guy here. All right. So usually I say cosine of theta equals 1/2 e to the j theta plus e to the minus j theta, like so. Right? We usually deal with that relationship a lot. What it says in words, basically, and where I ended up with last time, as I said, the cosine function can be thought of as basically two vectors that are rotating in different directions. Now, when I say rotating, it comes into the fact that I usually think of theta being something that is changing over time. All right, so in other words, I'm writing this as cosine omega, or theta equals omega t plus phi. In other words, the angle of this thing changes with respect to time. That's the way we think of cosine and sine waves. Why do we care about that stuff? Well, because most of the real things that we're trying to work with, whether it's a power system signal or whether it's a radio wave or an audio signal or something like that, most of those things can be represented as these cosines and sines. Okay. All right. So if I have something like this, all right, I got a couple of different ways. Okay. So I've got something like this, a e to the j theta, and I say theta equals omega t. All right. I think of that as this complex exponential vector that is moving over time. So let's say I've got this. Let's say I had 4 e to the j omega t like that. Okay. So I can write this as 4. Okay, I'll ask you guys. How would I expand that using the Euler's identity? 4 e to the j omega t. How do I expand that using the Euler's identity thing? I expand cosine. Yep. Cosine omega t plus what? J sine omega t. Okay. Like that. Okay. Now I say that this guy is a rotating vector. All right. So I want to understand that a little bit. 4 e to the j omega t. So let's 4 e to the j omega t. Usually what I say is that it's omega is a frequency. And what are the units of that frequency? When I say omega t, omega is a frequency. What are the units on that guy? Radians per second. It's radians per second. Yeah, so this guy is in radians per second. So it's basically, it ends up telling me how fast this vector is going to move. So let's do this a couple of different ways. Let's say I have 4 e to the j omega t, and let's say t equals 0. I'll do it here. Let's say t equals 0. When t equals 0, how do I draw 4 e to the j omega t when t equals 0? I'll just plug that in. So let's say I got 4 e to the, if a t is equal to 0, what does that become? So 4e to the j omega t. What's that become? Yeah, so it becomes 4e to the j 0. So if I expand that out with my Euler's identity, that's 4 cosine omega t. So what's that? Cosine omega t when t is equal to 0. 1. So this becomes 4 plus j 0. So time t equal to 0, this guy is a vector. In which direction? And I use that term kind of interchangeably, vector and complex numbers. I draw the complex number in the complex plane. That's like drawing a vector, right? Where does this vector sit? It's purely real, right? So here's 4e to the j 0. Okay. Now let's say time is advancing. So for sake of argument, let's say that this guy is advancing with a frequency of 1,000 radians per second. Okay. So let's say I come to a time when omega t is equal to 90 degrees. All right. What time would that be when omega t is equal to 90 degrees? How would I figure out that time when that happens? How do I calculate that? If this thing has a frequency of 1,000 radians per second. Yeah, I calculate and convert the 90 degrees to radians. So that basically would say, all right, let's do this. 1,000 radians per second times t equals 90 degrees, or t equals 90 degrees divided by 1,000 radians per second. I got to do a conversion here. So I'd say multiply that by pi radians over 180 degrees. And I would get some number. All right. I don't know what that number is, but I'd get some number for the time. And what would the units be on that time? Seconds. All right. Question is, when omega t is equal to 90 degrees, that means that this thing is equal to 4e to the j 90 degrees. All right. Where is that vector at that point in time? Where is that vector? How would I figure that out? If I told you 4e to the j 90, well, how would I figure that out? What tool do I know that I can use this e to the j anything? 4e to the j 90 degrees. How do I expand e to the j 90? Euler. So I say 4 cosine 90 plus j times 4 sine 90. What's the cosine of 90 degrees? 0. What's the sine of 90 degrees? 1. This guy is 4j. Where's that? Straight up. Okay. All right. So what happened here? So when t was equal to 0 seconds, this guy was the vector pointing that, right? Pointing purely on the real axis. By the time that the time moved up so that omega t was equal to 90 degrees, so whatever time this is, now that vector is pointing straight up. It rotated, right? As time advanced, it rotated. So which way did it rotate as I went from here to here? Which direction did it rotate? Counterclockwise, right? Counterclockwise. And call that the positive direction, right? Because angles increase positively from 0 degrees to 90 degrees, right? That's rotating counterclockwise is a positive change in angle. That guy, I say he rotated in the positive direction. How fast did he move there? How long did it take? Well, we calculated a time. What's causing this thing to rotate at a particular speed? Well, this omega value, this radians per second value, that's how fast this thing is moving. If I increase that value, this thing would rotate faster. All right, now what's going to happen if I get to omega t equal to 180 degrees? Well, now I have 4e to the j, what? 180. What's 4e to the j 180? What's that equal to? with using again the Euler's identity. How do I break that up? I say it's 4 what? 4 cosine 180 plus j times 4 sine 180. What's the sine of 180 degrees? 0. And what's the cosine of 180? -1. So this guy is -4. All right, where's that in the complex plane? Right, it's on the negative real axis. Okay. Now a couple of questions here. I want to do two things. First was I want to write this in polar form. So -4. You're not used to thinking about that, but -4. If I asked you if I said to you, what's the magnitude of this? What would you say it is? 4, not -4. Some of you will say -4. 4 is the magnitude. Magnitude is always positive. What's the negative mean? What is it? The angle, right? Yeah. So what's the angle in this case? 180. So I can write this as 4 angle 180 degrees, or I could write it as what? I could say 4 angle -180, right? I could write it that way too. Those are both acceptable. I could also say it's 4 angle 180 plus 360, right? That would also be acceptable, right? So there's a couple of different ways that you could put that in there. Right now, the other question I could ask is, what time would this happen? Well, if my omega was equal to 1,000 radians per second, and I said to myself, what time did that happen? I could say, when is omega t equal to 1,000? Sorry, times t. And when is that equal to 180 degrees? I do the same thing I did before, right? Basically, I would end up saying, when is t equal to pi radians divided by 1,000 radians per second? So whatever time that is when this would happen. If omega was equal to 100 instead of 1,000, would the time be the same? No, right? How would it take less time or more time if omega was a smaller number? It would take more time if omega was a smaller number, right? Because it's rotating slower, okay, is the idea. All right, so now simple, what am I going to do next? I'm going to say, what happens when omega t is equal to 270 degrees? Well, now I have 4e to the j 270 degrees. What's that going to be? I can expand that with Euler's identity again too, can I? I can just say 4 cosine 270 degrees plus j times 4 sine 270 degrees. What's that become? What's the cosine of 270? 0. Well, no, not 0. Sorry. Yeah, 0. Right? What about the sine of 270? -1. Right? So this becomes negative j 4 sine 270. All right. Which becomes -4. Like that. Okay. So negative j4, where's that? Straight down. Okay. Now, what happens when I get all the way around, right? So one revolution, technically, what ends up happening is I say omega t, what's omega t equal to when I've made one full revolution around? 360, right? Which is, if I want to figure out the exact time it happens, I got to say it's a 360. But it's the same as if I were at what angle? 0, right? So where's it going to point when omega t is equal to 360? Purely to the right, right? So the thing that happens, the thing that matters, if I want to figure out the exact time it's 360 or the exact time it's 720, right? Then I need to use those angles. But the important thing is whatever's happening between 0 and 360 is the same thing that happens between 360 and 720, right? It's basically, so this guy just keeps rotating around. Now, that just seems like a trivia fact that's probably useless. Like what I was saying last week is, this is really useful if I get into sort of a microcontroller, a DSP, and I'm trying to sort of process sine waves. And if I can keep them in this complex number form, actually, from a computer engineering perspective, it becomes a lot easier to play with those numbers. All right. From a circuits analysis perspective, it becomes a lot easier to play with these numbers as well. All right. So we're gonna learn more about them because they're really useful to us. Okay. So So in general, again, I use the term sine wave two different ways. All right. I use the term sine wave. Usually I say sine wave, but what I mean is in general a cosine or a sine. And my general way of representing everything is this guy here, a cosine omega t plus phi. Right? You're going to learn we usually take a sine wave and I convert it to a cosine wave. There's a reason why we do that. It makes things a lot simpler. It's a sort of a standard notation that we use. You're going to see that in 2112 if you're taking that this semester. Okay. So basically, I have two ways of thinking of this thing. All right. I basically have two parts. I can think of it as two rotating complex exponentials, or I can think of this thing as the real part of some complex numbers. I'm gonna dive into these things a little bit more here in the next 30 minutes or so. All right. But basically what we just talked about, again, I kept it simple. I said, what happens if I have 4e to the j omega t, right? So I'm going to keep it simple for now, but I want to expand that into something a little bit more complicated as we go. All right. So I'll come back to that. Basically, what I'm saying is both sine and cosine can be thought of as the combination of two vectors in the complex plane that move over time. One of them moves in the counterclockwise direction. One of them moves in the clockwise direction. So forward or positive is the counterclockwise. Backwards or negative is the clockwise direction. So again, if I had in my example e to the j omega t, I say that that's 1/2 e to the j omega t plus 1/2 e to the negative j omega t. Which one is the counterclockwise mover and which one is the clockwise mover? Yep, this guy here is clockwise. Sorry, this is counterclockwise, right? This is positive. This is the clockwise or negative or backwards, all right? So this is counterclockwise, positive, or forward. This is clockwise, negative, or backward, whichever way you want to refer to it as, okay? All right, so I kind of ended up with this example on Thursday, right? And I said, well, what if I have 4 cosine 1000t like this? All right, 4 cosine 1000t. So I can think of 4 cosine 1000t. How do I use that relationship there to write this guy? In other words, how can I write 4? What did I do? That's not what I meant to write there. That's what I should have written. Cosine omega t is equal to that plus that, right? How do I use that result here? How do I use this result here to write 4 cosine 1000t? How do I write 4 cosine 1000t and using this result? What would this summation become in that case? Yep. This would be plus 2e. Yeah. Yep. Yeah, so it's a minus 1000 up in the exponential, right? But it's a plus in terms of the way I deal with it. Okay. So what I showed here is basically a couple of things. What I showed is this vector, and their sum. Okay. And I did this specifically at t equal to 0. Okay. And then down here, what I have is the real and the imaginary part of the sum. Okay. The real and the imaginary part of the sum. So let's see, where do I see those vectors here? Well, 2e to the j 1000t, when t equals 0, what's true about both of these guys when t equal to 0? What's this equal to? When t is equal to 0, what's true about 1000t and negative 1000t? Both equal to 0. So this guy basically is 4 equals 2 plus 2. All right, so basically what I have here is I've shown 3 vectors. Well, it's kind of hard to tell. Here's one of them, the summation there. So you can see the length of that vector is 4. And then the 2 and 2 are where? Right there. All right. And again, hard to tell the difference between the two of them because they're exact same size. They're sitting on top of each other. Now, what I've done is I've shown the real and the imaginary part of the sum at that point in time. So the summation, if I had a vector, the vector 4 there, what's the real part of 4? 4. What's the imaginary part of 4? 0, right? So basically the imaginary part here, t equal to 0, is 0. The real part is 4. Okay, so I'm going to keep going. This is where we ended up the other day. And I said, well, what happens when t equals, or omega t is equal to 30 degrees? Okay, so omega t is equal to 30 degrees. Okay. All right, so I've got omega t equal to 30 degrees. So what I did here is I said, well, if my omega is 1,000, then I solved for t, and I said, well, that basically happens. Omega t is equal to 30 degrees at t equal to 524 microseconds. All right, 524 microseconds. How would I write that in terms of seconds? Make sure we're all on the same page with that. 524 what? 10 to the minus what? 5.24 times 10 to the minus 6. Right. In engineering terms, usually we'll write that as 524 times 10 to the minus 4. It's usually how I write that. All right. I could write that either way. Okay. So 5.24, sorry, what did I just do? 524 times 10 to the minus 6. All right. 524 times 10 to the minus 6. Right. So microseconds is 10 to the minus 6. All right. Or what you guys, 5.24 times 10 to the minus 4. Right. That would be the other way to write that. All right. Both of those are equivalent to each other. 524 microseconds is how I put that. All right. So what I did here is I said, all right, well, let's expand this guy out using that Euler's identity. So you guys told me previously that if I had 4e to the j theta, that's 2e to the j theta plus 2e to the minus j theta. All right, that became this. Now, what I'm showing again is both the summation as well as the two individual components. So 2e to the j 30, where is that in this picture that I drew over here? Where's 2e to the j 30? Which of those three vectors there? I got three of them in that picture. It's the upper one, right? 2e to the j 30 is here, right? 2e to the negative j 30 is here. How can you tell? Yeah, so the clockwise one is at 30 degrees. That should be up in the first quadrant. The counterclockwise there is sorry. The counterclockwise one is moving forward. The counterclockwise one is up in the first quadrant. The clockwise one moved into the fourth quadrant. The summation of those two added up. And what are they equal to? They equal to 4 cosine 30 degrees. Okay. And so if I looked at this over time, if I look at the real part, the summation of those things is entirely real. Looking at that picture, right? What I see is basically 2e to the j 30 going up, 2e to the negative j 30 going down. If I add those two together, do they have an imaginary part? No. Those imaginary parts cancel each other and they get longer, right? The summation is longer. So basically, what I have down here is the real and imaginary part of the sum. The imaginary part has no sum. It's 0. What's the real part? 4 cosine 30, which if I went and did that, that's 4 square root of 3 over 2. I wanted to calculate that. All right. So if I keep moving, right, and I say, what happens when omega t is equal to 60 degrees? Right? When omega t is equal to 60 degrees, if omega is equal to 1,000, I say, well, when is 1,000 t equal to 60 degrees? I solve for that, and I find it's 1.0472 milliseconds. So what is that in seconds? 1.0472 milliseconds. Well, how would you write that? 1.0472 times 10 to the minus 3 seconds. All right. So what did I do? I said 4 cosine 60 is 2e to the j 60 plus 2e to the negative j 60. So that I got from Euler's identity. And what am I showing? So the top vector, the vector in the first quadrant, is the 2 angle 60. The one in the fourth quadrant is 2 angle negative 60. The summation of them is 4 cosine 60 degrees, which is entirely real. So what I'm showing is the real part is here, the imaginary part is 0. What's going to happen when I get to 90 degrees? What's true about these two vectors, this one and this one? Where are they going to be when I get to 90 degrees? Where are they going to point? Up and down, right? So at 90 degrees, they're pointing up and down. What's the summation of those two things going to be? Well, I got one going up, one going down. What's the sum? 0, right? So the sum is 0. So if I looked at this, again, it happens at this particular time. If I solve for it, for that frequency, it happens at that time. What I see is the imaginary part still 0. The real part is 4 cosine 90, which is 0. What's going to happen if I get to 270? Or sorry, let's do 180 first. What happens if I get to 180? What happens if I get to 180? So if omega t was equal to 180, where would the two vectors point at 180? At 180, they would both, so they're both rotating. Let's watch them as they rotate, right? So at t equal to 0, they're both pointing in the real direction. Now again, they're rotating in opposite directions. So 30 degrees, one's going up 30 degrees, one's going down 30 degrees. At 60 degrees, one's going up 60, one's going down 60. 90 degrees, one's going up 90, one's going down negative 90. What's going to happen at 180? Both going to point at 180. I didn't do that one. I skipped right ahead to 270. All right, at 180, they would basically both be pointing in the negative real direction. At 270, what happens? Well, I get that picture. Which one is which? All right, so at 270, one's up and one's down. Which one's up and which one's down? So the one that was rotating in the positive direction is now down here, and the one that's rotating in the negative direction is up there. All right, the summation is still entirely real. Okay, so what we did was, if I keep going, if I go back to 360 degrees, which happens at this time, what's this time also going to be equal to? What do we call that? When I get back to 360 degrees, I get that time. What is that always equal to? What do I call that time? The period, right? One period is how long it takes to make one rotation around that plane. All right. So what I've got here again, this is the real part. This is the imaginary part. If I looked at this, this is kind of the important thing that we've seen as I've gone through, right? If I told you in general, all right, if I had 4 cosine 1000t, let me write it this way. If I have 4e to the j 1000t, that's equal to 4 cosine 1000t plus j times 4 sine 1000t. Okay. If I ask you, what's the real part of that thing? What's the real part of 4e to the j 1000t? We usually write that with these brackets. Real part, RE and IM, real and imaginary, the way we rewrite those two operators. If I say, what's the real part of 4e to the j 1000t? What is the real part of that? So 4e to the j 1000t is 4 cosine 1000t, left the t out, plus j times 4 sine 1000t. What is the real part of it? the cosine part, the 4 cosine 1000t. So, all right, basically what I end up with is I see that the real part of that expression is always cosine. That's actually what I have right here, right? I have the summation of the two vectors shown down here. The summation is entirely real. The real part of the summation tracks cosine as it moves along, right? And if you watch that, you would see as you watch the summation of the vector, so t equal to 0, the summation is entirely real, right? And it's pointing that way. At 30 degrees, the summation is entirely real. It's just a little bit smaller. 60 degrees, the summation is entirely real, and it's a little bit smaller. 90 degrees, the summation is entirely real, and it's equal to 0. I've tracked basically cosine as the summation, right? So basically, this gives us a couple of ways of thinking about this thing. All right, anytime I have a sinusoidal function, right? So a cosine omega t plus phi, I can think of it two ways. I can think of it as these two rotating vectors, or I can think of it as the real part of that thing. Now, again, I just made this a heck of a lot more complicated than what I just did. At least at first it looks that way. Why? Because I added this phi thing in there. So let's just make sure we're comfortable with what I'm saying here. So let's talk about this. So let's say I have a cosine omega t plus phi. And let me actually do it this way. Let's say I have a e to the j omega t plus phi. Like that. Okay. That I can expand out using Euler's identity. So I have a, help me expand that using Euler's identity. How do I expand that out? A cosine what? Omega t plus phi plus what? Plus j times a sine of omega t plus phi. Okay, so if I ask you what's the real part of a e to the j omega t plus phi, what's the real part of that? It's the cosine part. Okay. Now, the other thing that I did here is I said that this a e to the j omega t plus phi, let me see, get this out of the way. A e to the j omega t plus phi, this thing here, I can also write that out a little bit differently, right? If I have e to the a times e to the, well, sorry, e to the a plus b, how can I write e to the a plus b? E to the a times e to the b, like that. So what that says is a e to the j omega t plus phi, I can write that as a times what? So let's say it this way. I'll write it j omega t plus j phi, like that, right? So that's e to the a plus b. So I can write that as e to the a times e to the b. So I say a e to the j omega t times e to the j phi, like that. That's what I've written here. Okay. Now, the other thing that I did was I wrote out this part here, right? This is using that other form. So we have two things that we're using here. Let's go back for a second. Okay. I got two things that I'm using here. I have this notion for a second that e to the j theta equals cosine of theta plus j sine theta. I'm using this idea. And I'm also using e to the j theta over 2 plus e to the negative j theta over 2 is cosine of theta. using both of those ideas. Okay. All right. And I'm coming up with basically two different ways of thinking of this thing. Okay. So one way is to say that the cosine is the real part of this. I'm also saying that I can think of this sine wave as this cosine wave as being the sum of two vectors, one that is rotating in the positive direction, one that's rotating in the negative direction. Or it's the real part of one vector that's rotating in the positive direction. All right. So there's two ways of thinking about it. One is a vector that rotates only in the positive direction. The other is the sum of one rotating forward and one rotating backwards. All right, so we're going to look at examples of this, but basically I come up with a couple of terms, a couple of definitions of this. Something called static phasor and dynamic. If I use the term static versus dynamic, what does that mean when I'm talking in terms of time? Something is static versus dynamic. What's the difference? Static doesn't change with time, and dynamic does. Right? So a e to the j phi, whenever I have this thing, omega t plus phi, the phi is basically, we said it was the offset from where cosine is at t equal to 0. That's always a constant. It's always a number. So a e to the j phi, this is always going to be a constant. Whereas this guy is moving. All right? The dynamic phasor moves over time. The static phasor stays constant. Now, why do we differentiate between these things? We often use this in 2112, you use this a lot. All right? In 2112, you'll say, hey, I've got a circuit and I'm going to put cosine omega t plus 4 degrees into that thing. And that cosine omega t plus 4 degrees may be basically like an audio signal that you're trying to process. Solving to figure out what the circuit's going to do by saying it's a cosine, really difficult. But if I just track what happens to the angle and the phase, so the angle, sorry, phi and the amplitude, if I track what's happening with the amplitude and this angle phi going through a circuit, I can completely simplify all the differential equations and get rid of it. All right, so that becomes really, really useful in circuits. All right, and part of the reason why we focus on this. All right, we're going to see that as we go through the differential equation stuff in the next unit. For now, I want to say, okay, let's apply this. Let's say I have 4 cosine 1000 t plus 30 degrees. All right, I've got this guy. So that is the real part of something. So let's remember what we have. If I have 4 e to the j 1000 t plus 30 degrees. Okay. I can expand that with Euler's identity. How? I just think of this as theta here. If I do that, then I can write this as 4 cosine theta plus j times 4 sine theta. So what's that become? Help me write that out. Yeah. Plus j times. Yep. Yep. Like that. Okay. What's the real part of that whole thing? Yeah, this guy's the real part. So I'd say if I give you 4 cosine 1000 t plus 30 degrees, I would say it's the real part of 4 e to the j 1000 t plus 30 degrees. Like that. Okay. Now, I often don't write it that way. What's the other way? If I have 4 e to the j 1000 t plus 30 degrees, I can write that as 4 times e to the something times e to the something. How do I break that up? Okay. J 1000 t. Now again, I broke that up and then I kind of shifted. I commuted the e to the j 30 to the front. The reason I did that is because both of these things here are static. This is the part that adds the time dimension. So what I call the static phasor is the 4 e to the j 30. That static phasor is really important for me when I get into 2112. All right. 2112, if you're in that now, you're going to be using that a lot. And oftentimes you'll just write it as 4 angle 30. All right. You won't use the E. In here in this class, because this is more math, I'm going to use the E to the J a lot. All right. But again, in 2112, usually we skip that and we focus purely on just the polar form. But the dynamic phasor, that's the whole thing. That's the 4e to the j 30 degrees times e to the j 1000 t. All right, it's that. And then I can say for this whole thing, this cosine is the real part of that dynamic phasor. Like that. All right, so what I want to do is there's one other way that I could write this too. I could also say that I have 4 e to the j theta. Let's try to do it this way. 4 cosine theta. Using that other way we had to represent cosine, I could say that that's 4 over 2 e to the j theta plus 4 over 2 e to the minus j theta. If I plugged theta into that whole thing, it would become 2 e to the j 30 degrees times e to the j 1000 t plus 2 e to the minus j 30 degrees times e to the j negative 1000 t. All right, there's a lot of stuff going on here. I know you guys start glossing over e to the j, e to the j, e to the j, right? So what am I saying here? I'm saying I can think of this cosine wave 2 different ways. One is as the real part of this, okay? One is as the summation of this guy and this guy, all right? Both equal ways of thinking of them, both a way of thinking of them in terms of complex numbers. Nothing wrong with thinking of them either way. Nothing wrong with not even knowing anything about complex numbers, right? But it's useful to me, again, later on in your other classes to be able to think of them both in terms of these ways. All right, so what am I doing here? So I took 4 cosine 1000 t plus 30 degrees. And here I'm showing 2 things, okay? What 2 things am I showing? Well, I'm specifically showing what's happening here at t equal to 0 degrees. All right, so if I have 4 cosine 1000 t plus 30 degrees, at t equal to 0, what does that equal to? Okay, so let's just remind ourselves. We said on the previous slide, 4 cosine 1000 t plus 30 degrees. It has associated with it a static phasor and a dynamic phasor. The static phasor is 4 e to the j 30 degrees. We just established that. The dynamic phasor we established was 4 e to the j 30, e to the j 1000 t. So here's 4 e to the j 30 degrees, e to the j 1000 t. Again, the word dynamic versus the word static. What's the difference between dynamic and static? Dynamic does what? Changes with time. Now, at this particular case, I'm saying at t equal to 0. Okay? At t equal to 0. So, all right, let's think about this. At t equal to 0, omega t plus phi is what? 1000 times 0 plus 30 degrees. What's that equal to? 30 degrees. Okay, so at this particular point in time, the dynamic phasor and the static phasor are exactly the same. Okay, where is that shown here? I showed 2 vectors in this picture, this one and this one. What have I shown here? 4e to the j 30 degrees. Where is 4e to the j 30 degrees? Which of those 2 is it? Yeah, the one pointing up. This guy here is 4e to the j 30 degrees. And actually, it's both, in this particular case, at this time, this guy is both the static and the dynamic. Right? I mean, they're both plotted. You can't see that one's on top of the other. What's this thing down here? What's the other one that's pointing straight over? What have I shown? What have I shown? Well, that's the real part of 4e to the j 30 degrees. How can I tell that's the real part? Because it points exactly over to where that guy ends, right? And it's pointing straight over with an angle of 0 degrees. That's the real part. So when time advances, let's say I get to, in this particular case, let's say I get to omega t plus 30 degrees. All right, so let's do it this way. Theta equal to 1000 t plus 30 degrees. Let's say I get to the point where that combination of those two things is equal to 60 degrees. Sorry. What time is it when that combination equals 60 degrees? Well, I can solve for that time. And at 524 microseconds, that's when that combination is 60 degrees. So the dynamic phasor we said before is always 4e to the j 30 degrees times e to the j 1000 t. The static phasor is always what? All right, if I had 4 cosine 1000 t plus 30 degrees, dynamic phasor always is this. What's the static phasor? Yeah, the 4e to the j 30. Okay, not 300. 4e to the j 30. Now, at this particular time, at 524 microseconds, the static phasor has a theta value equal to 60 degrees. Okay, so basically, the static phasor, which is 4e to the j, I'll write it this way, 1000 t plus 30 degrees, is apparently 4e to the j 60 degrees. All right, so on this graph, I've drawn 3 different vectors now. What 3 vectors have I drawn? Yeah, dynamic, the static, and the real part of the dynamic. So this is the, where's the real part? Yep, this is the real part of the dynamic phasor, 4e to the j 30 degrees times e to the j 1000 t. Smaller than it was here, right? Smaller than it was previously, right? As it should be, because it's tracing out cosine, okay? What's this? Which one is this? Is that the static or the dynamic at this time? All right, so let's just check ourselves. The static and the dynamic have the same length. Both have a length of 4, right? Static has an angle of 30, dynamic has an angle of 60. So which is which? This one's the static, and this one is the dynamic. Down here, I'm showing what the real part does over time, okay? Then I keep moving, all right? What happens when theta is equal to 90 degrees? Well, as always, I have the dynamic phasor as 4e to the j 30 degrees times e to the j 1000 t. So at that particular point in time, this becomes 4e to the j 90 degrees, like that. What's the static phasor always? What's the static phasor always? 4e to the j 30. So which ones have I shown in this picture here? This is the static, right? Because it's at a 30-degree point. This guy over here is the dynamic, right? So at this particular point in time, the dynamic is rotated so that it's pointing straight up, has an angle of 90 degrees, okay? Where's the real part? 0. The real part is 0 because it's always the real part of the dynamic one, right? And the dynamic one's pointing straight up, so it's purely imaginary, so it has no real part. So the real part I'm seeing looks like it's tracing out a cosine, okay? I keep going. All right, now in this particular case, I say, what happens when theta is equal to 120 degrees? So what's the dynamic phasor? Always the dynamic phasor is 4e to the j 30 degrees times e to the j 1000 t. At this particular point in time, it's 4e to the j 120. All right, what's the static phasor? What's it always? 4 with an angle of 30 degrees. So 4e to the j 30 degrees. So I got 3 things drawn again. Where's the static phasor? Yep. This guy here with a length of 4 and an angle of 30. Where's the dynamic? Well, he's right here. How do I know he's right there? What's his angle? 120. Okay. What's this? Well, this is the real part of the dynamic. The real part of the dynamic. Right? So in other words, the real part of 4e to the j 120. And I can see that guy, again, if I take the real part, it's tracing this out. So I do a couple more here. All right. And I said, what happens when it's 210 degrees? At 210 degrees, without me writing anything here. So what's what? Which one's the static of this one, and this one? Which one is the static? This is the static, yep. Which is 4e to the j, 30 degrees. Which one's the dynamic? This one. This is the dynamic, which is 4e to the j, 30 degrees, times e to the j, 1,000 t, right? Which at this particular point in time is 4e to the j, 210 degrees. Okay. This is the real part of the dynamic. Like that. Okay. And I'm just trying to show that relationship. So here I keep going with it, this 300 degrees, and then I take it around until it's equal to 30 degrees again. So technically, this was 300. This is 390 degrees. I wrote this statement here, 390 is equal to 30. That doesn't look right, does it? It is right. 390 is the same angle as 30 degrees, right? So if I want to figure out the exact time that this happens, I would need to solve omega t plus 30 degrees equals 390. But I know that it's going to happen exactly, that tells me the exact time, right? But I know that whatever happens at 30 degrees and what happens at 390 degrees is going to be exactly the same thing because those are the same angle, right? This process just kind of keeps repeating itself. All right. So in summary, basically what I see is as I advance through one period, right, the dynamic phasor traces out a circle. All right. The real part of the dynamic phasor traces out a cosine waveform, and the static phasor doesn't move. And I say that doesn't seem special, but it's useful in circuit analysis. Okay. All right. That's a lot to digest. All right. And so I don't want to say too much more, right? But I do want to talk about one thing real quick to kind of jumpstart you a little bit further on the homework. All right, this is something you would have learned in high school. Let's say I have x to the fourth plus 1 equals 0. All right, so, and I asked you to solve for x. All right, so if I had x to the fourth equals 1, what's x equal to? 1, right? But how many roots, and you should know that, right? I said for any polynomial, though, it's supposed to have as many roots as whatever the order of the equation is, right? So there's actually 4 roots to this thing. And they're not 1, 1, 1, 1, and 1. Did I say that 4 times? I think I said 5 times. 1, 1, 1, 1. They're not 4 ones repeating. So they're supposed to have 4 unique roots. How would I figure that out? Right? I know x equal to 1 is one value. I can do that. Like that. How else can I do this? Factor it how? Plus 1. I don't have that though. I got x to the fourth minus 1. Yeah. So how else could I write this? I think you must have you could say from like x to the fourth minus 1 to the fourth, or the identities. All sorts of ways you can start to think about it. I'm going to start thinking about the number 1 as e to the j 360 degrees. Or let's do it this way, e to the j 0 degrees. Right? That's the number 1. That would have burnt your brain in the first grade, right? Right? 1 is equal to e to the j 0. How else can I write that? Well, I can also say it's e to the j 360 degrees. Right? I can also say it's equal to what? E to the j 720 degrees. I can also say it's equal to what? What's 720 plus 360? That's 1080, right? So now, what can I say I get? X could be equal to what? E to the j 0 or 1. Could also say that I get what? E to the j 360 degrees divided by 4, right? I could also say it's equal to E to the j 720 divided by 4. I could also say it's equal to E to the j 1080 divided by 4, right? If I did this, what I would end up with is basically, I'll call this x1, call this x2, call this x3, and call this x4. Where would those guys point? So E to the j 0 degrees, that's a vector. Where's it point? Purely real. So it's going to be this way. It's going to be the number 1, right? What about E to the j 360 divided by 4? What's 360 divided by 4? 90 degrees. Where's that guy point? E to the j 90. Straight up, right? What about his compadre here? E to the j 720 divided by 4. 720 divided by 4 is 180. So he'd be pointing over this way. And then where do you think the other one's going to point? Without even doing the math, straight down. This would be x1. This would be x2. This would be x3. This would be x4, right? In general, if I have x to the n equal to 1, I basically say that I have e to the j 360 like that. And I'm going to end up getting n roots. And so I end up thinking of it like this. My roots are 1 e to the j, and I did this in radians, e to the j 2 pi over n, 4 pi over n, all the way up like that. Okay? Pretty straightforward way of thinking about this. This isn't too hard. All right, we're gonna do examples of this on Wednesday, or not Wednesday, Thursday, when we meet again. I don't want to do anything more, but this concept should be pretty straightforward, what I just talked about here. All right, so I'll deal with that more. If you got questions, you can come up and ask. But I'm going to stop there rather than I burn your brain by eating up the next couple of minutes.